This is 11.4, the comparison test. So this is yet another test to determine whether a series is convergent or divergent. So in this case, we're going to look at two series, and if b of n is greater than or equal to a sub n, and b sub n is convergent, then that means a sub n is also convergent. And if b sub n is divergent and it's less than or equal to a sub n, then the series a sub n is also divergent. So let's see how this is going to work. So we have this series, so we want to compare it to a different one. So let's let b sub n equal to 1 over radical n. I'm choosing 1 over radical n because I see a radical n there. And this is easy to test. It's a p-series. Since 1 over radical n is divergent, it's a p-series with p equal to, 1/2. So we know if p is less than 1 or equal to 1, then it's divergent. And if it's greater than 1, it's convergent. And we also know that, let's see, 1 over radical n minus 1 is greater than or equal to 1 over radical n. Because the denominator is smaller, that makes the entire fraction bigger. Since this is true and this is divergent, then this one must also be divergent by the limit comparison test. By the limit comparison test, the series 1 over radical n minus 1 must also be divergent. Okay, so that's all you got to do. All right, let's check the next one. Okay, so for this one, we're going to start with saying that k sine squared of k over 1 plus k cubed is less than or equal to, well, since this is bounded by 1 and negative 1, and when you square it, it's going to be bounded by 1, we can say that it is less than or equal to this, because this is, when you square sine, it's the biggest values that it can take on is 1, and so this is true. All right, and then we also know that this is true because the denominator is smaller here, which makes the fraction bigger than this one because the denominator is smaller than this denominator. And then we can simplify this fraction. All right, and we know that 1 over k squared is convergent. Once again, it's a p-series with p equal to 2. That's what makes it convergent. Thus, since k sine squared k over 1 plus k cubed is less than or equal to 1 over k squared, the series, I'll just put a comma, the series k sine squared k over 1 plus k cubed must also be divergent by the limit comparison test. I'm sorry, by the comparison test. Did I say the wrong thing over here? Yeah, I should have said the comparison test up here as well. Sorry about that. So both of these are by the comparison test. All right, the limit comparison test is a different test. So I misspoke earlier. This is a limit comparison test. So for the limit comparison test, you're going to take two series once again. You're going to divide them, take the limit. If the limit is positive and a finite number, then they either both converge or they both diverge. So in this case, the idea is you want to divide by something that will make the exponents equal. So that would be 1 over n squared. Because when you multiply by the reciprocal, you're going to get n to the fourth, and you have n to the fourth. So that's the idea. So we're going to say, use a limit comparison test. Use the limit comparison test with a of n equals n squared plus n plus 1 over n to the fourth plus n squared, and b sub n equals 1 over n squared. And then we're going to take the limit of a over a sub n divided by b sub n, which is going to be I'm going to factor out an n squared from the denominator. And when I divide by 1 over n squared, I'm just going to multiply by the reciprocal. So when I multiply by the reciprocal, that's going to be n squared on the top. And then, as you can see, these two terms are going to cancel. And then you're going to be able to write the new limit as n squared plus n plus 1 over n squared plus 1. But now you can divide each term by n squared because that's the highest power of the denominator. And you're going to get the following. One plus 1 over n plus 1 over n squared. 1 plus 1 over n squared. These terms will all approach 0. So your limit is going to be 1, which is greater than 0. And that's what this says. If you end up getting a limit that's positive and it's finite, then they both converge or they both diverge. Since we know that this converges because it's a p-series with p equal to 2, that means that this also converges. Since converges p-series, also converges by limit comparison test. All right, let's look at this last one. So the bottom, if you were to expand this, not that you shouldn't, but if you did, it would be a cubic. So you need this to be a cubic, so that means that your b sub n is going to be 1 over n squared again. So use limit comparison test with a sub n equal to n plus 2 over n plus 1 cubed, and b sub n is 1 over n squared. So now we take the limit as n approaches infinity of a sub n over b sub n. That's going to be n plus 2 over n plus 1 cubed. And when you divide, once again, by 1 over n squared, you're going to be multiplying by the reciprocal, which means you're going to have the n squared there. Might as well distribute. Okay, now when you divide everything by n cubed, because that's the highest power of the denominator, you're going to end up with 1 plus 2 over n. When you divide this by n cubed, when you go into the parentheses, since it's cubed, you're really dividing the inside by n because of the exponent is already cubed. So you just need to go into the parentheses and divide by n, which is 1 over n cubed. These two terms will approach 0, and you're going to end up with 1, which is greater than 0. Thus, since 1 over n squared converges, it's a p-series again, the series n plus 2 over n plus 1 cubed also converges by the limit comparison test. And that does it.